go. What to do, party people? Oh, hold up. I gotta sign into this thing. Dang it. Okay. Oops. Okay. We live. All right, let's get this show on the road. All right. Hello, everybody. Welcome back into the channel. Hope you're having a wonderful day so far. Today, hold on, let's try this Twitch real quick. There we go. What am I doing? What are we doing, bro? Cool. All right. Whatever, everybody. Welcome back to the stream. Hope you're having a good day today so far. We're going to be back streaming some C Programming, a Modern Approach, 2nd edition by K.N. King. We've been reading Chapter 9 the day before. Yesterday I was doing some stuff after work. I had a lot of business to catch up on, personal business to catch up on. Stuff, life events going on right now, big life events. More to come soon. But yeah, so we are back here today reading some more C Programming, a Modern Approach, 2nd edition by K.N. King. Boom, boom, boom. We left off on 9.4, the return statement, last time. So, hope all is well, Let's go ahead and wait for some people to roll up in here, and we'll get started again. Finishing up Chapter 9 today. So we have 9.4. We're on page 202. We got to get to page... $214. Oh, easy. 12 pages. Let's go. I'm all for that. Okay. Welcome back, everybody. Let's get going here. I'm going to start the recording, and we'll get reading. All right, we're recording. Cool. Let's go ahead and get started. Okay. The cool. All right, guys, here we go. Let's get into this one. Section 9.4, the return statement. A non-void function must use the return statement to specify what value it will return. The return statement has the form return expression, semicolon. The expression is often just a constant or a variable, return 0, return status. More complex expressions are possible. For example, it's not unusual to see the conditional operator used in a return expression. Return n greater than 0, then return n, else return 0. So this so return if n is greater than or equal to 0, n, else 0. When this statement is executed, the expression n is greater than or equal to 0, return n, else 0 is evaluated first. The statement returns the value of n if it's not negative, otherwise it returns 0. If the type of the expression in a return statement does not match the function's return type, the expression will implicitly convert to the return type. For example, if a function is declared to return an int, but the return statement contains a double expression, the value of the expression is converted to int. Return statements may appear in functions whose return type is void. provided that no expression is given. Return in a void function. Putting an expression in such a return statement will give you hold on, so really quickly. Okay, so it'll force conversion. Interesting. Putting an expression in such a return statement will get you a compile time error. In the following example, the return statement causes the function to return immediately when given a negative argument. Void print int I. If I less than 0, return printf I. If I is less than 0, print int will return without calling printf. A return statement may appear at the end of a void function. Void print pun void. Printf to see or not to see, that is the question. Return okay but not needed. So this is an error, but that one's not. Why? Putting an expression in a return statement will give you a compile time error. In the following example, the return statement causes the function to return immediately when given a negative argument. If I is less than 0, print int will return without calling printf. A return statement may appear at the end of a void function. Oh, it just happens to be at the end, like specifically, like when all is said and done, you can return. It's okay to have a return when all is said and done at the end of a void function, but this has a return implicitly at this, at this stage, which is not allowed. Okay. Using return is unnecessary though, since the function will return automatically after its last statement has been executed. If a non-void function reaches the end of its body, that is, it fails to execute a return statement, the behavior of the if a non-void function reaches the end of its body, that is, it fails to execute a return statement, the behavior of the program is undefined. If it attempts to use the value returned by the function, some compilers will issue a warning such as control reaches end of non-void function if they detect the possibility of a non-void function falling off the end of its body. What does that even mean? If a non-void function reaches the end of its body, that is, it fails to execute a return statement, the behavior of the program is undefined if it attempts to use the value returned by the function. Some compilers will issue a warning. Oh, okay, got you. So if you have a void function, the behavior of the program is undefined if it attempts to use the value returned by the function. Oh, so if you return a value, I thought we'd never hit a return statement. So it just has some garbage value in there. Okay, let's take some notes here on 9.4. Hey, how's it going, PK? How's it going, Tim? Welcome back in. Hey, Creative Nook. Welcome. Appreciate you guys for joining me today. What's everybody working on? Are we just listening to the reading today? Are we working on a side project? What are our goals for tonight? Okay. Using non-void functions. Okay, so we'll say return, right? A statement that breaks a function or stops a function and returns back to where the function was called with any values, any value following the return statement, a return keyword. Right? The expression is just often a constant or variable. We can use ternary conditional operators here, a ternary expression. So the return will, if we'll say implicit converted return type. So if the type of the expression expression in a return statement doesn't match the function return type, the expression will be implicitly converted to the return type. Cool. Nice. Return statements may appear in functions whose type is void, that no expression is given. We'll say return statements may appear in functions whose return type is void. Cool. Provided that no expression is given. This would be just like, okay. Cool. Nice, Tim. Doing Java creative? Nice. Here we go, boys. We grinding. So, cool. Whatever else. Okay, let's keep rolling. (9.5) program termination. Since main is a function, okay. 9.5 program termination. Since main is a function, it must have a return type. Normally, the return type of a main is int, which is the why. Gosh, dude. Since main is a function, it must have a return type. Normally, the return type of main is int, which is why the programs we've seen so far have defined main in the following way: int, main, void, so on and so forth. Older C programs often omit main's return type, taking advantage of the fact that it traditionally defaults to int. Omitting the return type in C99, omitting the return type of a function isn't legal in C99. So it's best to avoid this practice. Omitting the word void in main's parameter list remains legal. But as a matter of style, it's best to explicit. Oh my gosh, dude. Sorry. C99. Omitting the return type of a function isn't legal in C99. So it's best to avoid this practice. Omitting the word void in main's parameter list remains legal. But as a matter of style, it's best to be explicit about the fact that main has no parameters. We'll see later that main sometimes does have two parameters, usually named argc and argv. The value returned by main is a status code that in some operating systems can be tested when the program terminates. Main should return 0 if the program terminates normally. To indicate abnormal termination, main should return a value other than 0. Actually, there's no rule to prevent us from using the return value for other purposes. It's good practice to make sure that every C program returns a status code even if there's no plans to use it, since someone running the program later may decide to test it. The exit function. Executing a return statement in main is one way to terminate a program. Another is calling the exit function, which belongs to the standard library.h. The argument passed to exit has the same meaning as main's return value. Both indicate the program status at termination. To indicate normal termination, we'd pass 0, exit 0. Since 0 is a bit cryptic, C allows us to pass exit success instead. The effect is the same, exit exit underscore success. Passing exit underscore failure indicates abnormal termination. Exit underscore failure. Exit success and exit failure are macros defined in the standard library.h. The values of exit success and exit value are implementation defined. Typical values are 0 and 1 respectively. As methods of terminating a program, return and exit are closely related. In fact, the statement return expression in main is equivalent to exit expression. The difference between return and exit is that exit causes program termination regardless of which function calls it. The return statement causes the program termination only when it appears in the main function. Some programmers use exit exclusively to make it easier to locate all exit points in a program. Got you. So return when used in main exits the program, but return when used in other functions does what a normal return statement does and returns that value. Whatever's returned in main is inferred as the status code, right? Okay, interesting. All right, let's make some notes here. So we'll say omitting return type. We'll say older C programs often omit the main return type, the main function return type, the main functions return type. In C99, omitting the return type of a function is illegal. Okay. Okay, cool. Nice. Then we'll go here and do the exit function. So the exit function, exit function. Executing a return statement in the main is one way to terminate a program. Another is calling the exit function, which belongs to standard I/O. A function within the standard IO.h right? Oh, sorry, standard library. With arguments passed to exit that have the same meaning as main return value. Both indicate the program's status at termination. Cool. So we'll say exit 0, which is normal termination, and then exit 1, which is abnormal termination. Exit 1. So also exit like greater than 0, right? We can also say, we'll say exit success and exit, failure. Are macros defined within the standard IO or standard library .h header file that are implementation defined with typical values of 0 and 1. Okay. Nice. So we'll say so we'll also say when used in main, the return statement exits the program. Take that. Nice. And then do all right, cool. Okay. Main function. Nice. All right, let's keep pushing. All right, last section here, and then your boy is tired from work, building matrices and getting going for another large-scale project. So lots of work going on here. I've been grinding. Okay, hence why I'm late today. 9.6, recursion. A function is recursive if it calls itself. For example, the following function computes n factorial recursively using the formula n factorial equals to n times n minus 1 factorial. Int fact takes in int n. If n is less than or equal to 1, we're going to return 1, else return n times fact n less than 1. Some programming languages rely heavily on recursion while others don't even allow it. C falls somewhere in the middle. It allows recursion, but most C programmers don't use it that often. To see how recursion works, let's trace the execution of the statement. I equals to fact 3. Here's what happens. Fact 3 finds that 3 is not less than or equal to 1, so it calls fact 2, which finds that 2 is not less than or equal to 1, so it calls fact 1, which finds that 1 is less than or equal to 1, so it returns 1, causing fact 2 to return 2 times 1, which equals to 2, causing fact 3 to return 3 times 2, which equals to 6. Notice how the unfinished calls of fact pile up until fact is finally past 1. At that point, the old calls of fact begin to unwind one by one until the original call, fact3, finally returns with the answer 6. Here's another example of recursion. A function that computes n. Here's another example of recursion. A function that computes x to the power of n using the formula x to the power of n equals to x times x to the power of n minus 1. Int power takes in int x and int n. If n is equal to 0, return 1, else return x times power of x and n minus 1. The call power 5.3 would be executed as follows. Power 5.3 finds that 3 is not equal to 0, so it is calls power 5.2, which finds that 2 is not equal to 0, so it calls power 5.1, which finds that 1 is not equal to 0, so it calls power 5.0, which finds that 0 is equal to 0, so it returns 1, causing power 5.1 to return 5 times 1, which equals to 5, causing power 5.2 to return 5 times 5, which equals to 25, causing power 5.3 to return 5 times 25, which is 125. Incidentally, we can condense the power function a bit by putting a conditional expression in the return statement. Return if n is equal to 0, 1, else x times power of x n minus 1. Both fact and power are careful to test a termination condition as soon as they're called. When fact is called, it immediately checks whether its parameter is less than or equal to 1. When power is called, it first checks whether its second parameter is equal to 0. All recursive functions need some kind of termination condition in order to prevent infinite recursion.
You're not that guy, pal. Trust me. You're not that guy.
Wisdom broke up the,
you? Absolutely.
the reading. Shoot, thanks for the sub, bro. Vala, I appreciate you. All right, we got to read that one again. Both fact and power are careful to test a termination condition as soon as they're called. When fact is called, it immediately checks whether its parameter is less than or equal to 1. When power is called, it first checks whether its second parameter is equal to 0. All recursive functions need some kind of termination condition in order to prevent infinite recursion. Nice. And this should wrap up the chapter. Yeah, getting close. Okay, almost there. The quicksort algorithm. Hold on. Hold on one second. All right, cool, we're good. Sorry. All right, let's keep going here. The quicksort, the quicksort algorithm. At this point, you may wonder why you're bothering with recursion. After all, neither fact nor power really needs it. Well, you've got a point. Neither function makes much of a case for recursion because each calls itself just once. Recursion is much more helpful for sophisticated algorithms that require a function to call itself two or more times. In practice, recursion often arises naturally as a result of an algorithm design technique known as divide and conquer, in which a large problem is divided into smaller pieces that are tackled by the same algorithm. A classic example of the divide and conquer strategy can be found in the popular sorting algorithm known as quicksort. The quicksort algorithm goes as follows. For simplicity, we'll assume that the array being sorted is indexed from 1 to n. I hate when they do this. 1. Choose an array element E, the partitioning element. Then, rearrange the array so that elements 1 through I less than 1 are less than or equal to E. Element I contains E, and elements I plus 1 up to n are greater than or equal to E. Sort elements 1 up to E, right, which is I minus 1, by using quicksort recursively. Sort elements 1 through I less than 1 by using quicksort recursively. Sort elements I plus 1 through n by using quicksort recursively. After step 1, the element E is in its proper location. Since the elements to the left of E are all less than or equal to it, they'll be in their proper places. Once they've been sorted, in step 2, the similar reasoning applies to the elements to the right of E. Step 1 of the quicksort algorithm is obviously critical. There are various methods to partitioning an array, some much better than others. We'll use a technique that's easy to understand but not particularly efficient. I'll first describe the partitioning algorithm informally later. Later, we'll translate it into C code. The algorithm relies on two markers named low and high, which keep track of positions within the array. Initially, low points to the first element of the array, and high points to the last element. We start by copying the first element, the partitioning element, into a temporary location elsewhere, leaving a quote-unquote hole in the array. Next, we move high across the array from right to left until it points to an element that's smaller than the partitioning element. We then copy the element into the hole that points we then copy the element into hole that we then copy the element into the hole that low points to, which creates a new hole pointed to by high. Now we move low from left to right, looking for an element that's larger than the partitioning element. When we find one, we copy it into the hole that high points to. This process repeats with low and high taking turns until they meet somewhere in the middle of the array. At that time, both will point to a hole. All we need to do is copy the partitioning element into the hole. The following diagram illustrates how quicksort would sort any array of integers. The following diagrams illustrates how quicksort would sort an array of integers. Let's start with an array containing 7 elements. Low points to the first element, high points to the last one. So our low, which is our low index, points to the first, and our high points to the last. Note that low is not pointing to the highest value here in the array, or second highest, right, or third highest, whatever. It's just the low index. The first element, 12, is the partitioning element. Copying it somewhere else leaves a hole at the beginning of the array. Now, we compare the element pointed to by high with 12. Since 10 is smaller than 12, it's on the wrong side of the array, so we move it to the hole and shift low to the right. Low points to the number 3, which is less than 12, and therefore doesn't need to be moved. We shift low to the right instead. And since 6 is also less than 12, we shift low again. Low now points to 18, which is larger than 12, and therefore out of position. After moving 18 to the hole, we shift high to the left. High points to 15, which is greater than 12, and thus doesn't need to be moved. We shift high to the left and continue. So our high now points at 7. High points to 7, which is out of position. After moving 7 to the hole, we shift low to the right. Low and high are now equal, so we move the partitioning element to the hole. At this point, we've accomplished our objective. All elements to the left of the partitioning element are less than or equal to 12, and all elements to the right are greater than or equal to 12. Now that the array has been partitioned, we can use quicksort recursively to sort the first 4 elements of the array, 10, 3, 6, and 7, and the last 2, 15, and 18. Program, quicksort. Let's develop a recursive function named quicksort that uses the quicksort algorithm to sort an array of integers. To test the function, we'll have main read 10 numbers into an array called quicksort. To test the function, we'll have main read 10 numbers into the array, call quicksort to sort the array, then print the numbers in the array. Enter 10 numbers to be sorted. 10 numbers are entered. In sorted order is the sorted order of numbers. Since the code for partitioning the array is a bit lengthy, we'll put in some separate functions named split. Sorts an array of integers using quicksort algorithm. Include the standard io.h, define n to be 10, void.
You're not that guy, pal. Trust me. You're not that guy.
Here we go.
Okay. Okay? You? Absolutely.
Thank you so much for the sub. I appreciate you so much, Jagan. You're the man. You're the boss. Welcome. Okay, quicksort. Sorts an array of integers using quicksort algorithm. We include the standard io.h and we define n to be 10. We have a void function, quicksort, which takes in int array. We have a quicksort function which returns a void type, has an array element of integers, int low and int high. We have a function int split, which takes in an array of integers, a low int and a high int. And then we have our main function, where we define array A to be a size n, and we define integer I. Or declare, rather, right? Printf is equal to enter %d numbers to be sorted, and we put in the macro n. For I equals to 0, while I is less than n, I plus plus, scanf the numbers that the user enters into the array A at index of I. We're then going to call quicksort on the array with 0 being our low and n minus 1 being our high, and printing the values. We then have our quicksort function, which takes in the array a low and a high. We declare int middle. We say if low is greater than or equal to high, we return, meaning that our low either became at equal to high or crossed over. And middle is equal to split the array A and low and high. Then we call quicksort on the left half and call quicksort on the right half recursively. So our split function is here. We take in the array low and high. We have our partitioning element, which is the array index of low. Right? We infinitely loop here. While low is less than high, and the partitioning element is less than or equal to the array at index of high, we continually decrease high. If low is greater than or equal to high, we will break. Else we will, well, not else, so sorry. If low is greater than or equal to high, we'll break. And then the array at index of low plus plus is equal to array at index of high. So this increases our low in line here after this is called, right? So we'll use our current value of low, and then after this line, it'll increase. While low is less than high, and the array at index of low is less than or equal to partitioning element, we're going to continually increase the low, so the inverse of this above statement for the partitioning element relation to the high versus low. If the low is greater than or equal to the high, we will break. And at array index of high minus minus, which equals to array index of low. Once this loop breaks, we will set array at index of high equals the partitioning element and return high. Although this version of quicksort works, it's not the best. There are a number of ways to improve the program's performance, including improving the partitioning algorithm. Our method isn't the most efficient. Instead of choosing the first element in the array as a partitioning element, it's better to take the median of the first element and the middle element and the last element. The partitioning process itself can also be sped up. In particular, it's possible to avoid the low less than high tests in the two while loops. Using a different method to sort small arrays. Instead of using quicksort recursively all the way down to arrays with one element, it's better to use a simpler method for small arrays, those with fewer than, say, 25 elements. Making quicksort non-recursive. Although quicksort is a recursive algorithm by nature, and it's easiest to understand in recursive form, it's actually more efficient if the recursive is removed. For details about improving quicksort, consult a book on algorithm design such as Algorithms in C, Parts 1 through 4, Fundamentals, Data Structures, Sorting, and Searching. And now we've reached the Q&A here, so let's go back and take some notes on recursion. A recursive function, so recursive function. A function is recursive if it calls itself. Take some examples here. Some programs rely heavily. And then we'll take this example here, which is really good. Yeah, I'm gonna take all that, even the text. I like that little footer. This is a really great example of just showing it. Okay, and then let's do this one as well. Copy image. It's right there. And let's grab this guy here. So, cool. And let me make sure that that first image that we took, the image 17, does not. So we want it to be, no. Oh yeah, we do. We don't have the formula, so I'm gonna take, okay. All right, cool. Noise. All right, so then let's go down here and we'll make a note here for the termination condition. As soon as they're called, a test that is evaluated as soon as a recursive function is called to determine to determine to either terminate the recursive calls or continue to recurse. Is recurse a word? So this is to all recursive functions need some kind of termination condition in order to prevent infinite recursion. Cool. This is C Programming, a Modern Approach, 2nd edition by K.N. King. Appreciate you so much for being here. Welcome. You guys are new here. My name is Michael. I'm 26 years old, about to turn 27 this Friday. Happy birthday to me, I guess. Gonna be, yeah, we are graduated college back in 2021. I have a degree in human biology, minor in chemistry. We're teaching ourselves how to code in Python and now in C programming. C for about, well, we just started learning C a little bit ago, but we've been teaching ourselves programming in general for a little over a year and a half now. It's been quite fun. We've been doing this after my 9-to-5 job as a chemist for a biotech company. Cool. Let's keep rolling here. Appreciate you guys joining me as we read C Programming, a Modern Approach, 2nd edition by K.N. King. We just finished the chapter. We still need to read the Q&A to wrap it up, but we're just going over the notes of the last section here. So we'll say quicksort algorithm. A classic example of popular a classic example of the divide and conquer strategy can be found in the popular. A sorting algorithm. So a sorting algorithm that is a classic example of divide and conquer. An example of the divide and conquer technique. Okay. So we'll say divide and conquer. Large problems are divided into smaller pieces and pieces that are tackled by the same algorithm. Okay. So the quicksort algorithm goes as follows. So I want to do... So, this sucks. I hate how they index it from 1 in these examples sometimes. Just throws everything off. Like, just stick to the mojo. So we'll just go like this, I guess, and say, like, note. Note array example is ordered is okay. All right, cool. Honestly, these examples are really good. So am I a hack note taker by just taking these? Like, this is like, there's literally no better notes I can take than just a picture of this. In all honesty, it's not the code, right? I'm not going to copy the code into the notes, but this is like pseudocode basically. Okay, so now this is just the code given here. Yeah. So we'll say improving quicksort. Number 1 would be improving the partitioning algorithm. Number 2 would be using a different method to sort small arrays, let's say less than or equal to 25 elements. And then we'll say 3, making quicksort non-recursive. So although quicksort is recursive, easiest to understand recursive form is actually more efficient if recursion is removed. Okay, cool. Let's read these Q&A questions and then we will bounce. Q&A. Some C books appear to use terms other than parameter and argument. Is there any standard terminology? As with many other aspects of C, there's no general agreement on terminology, although the C89 and C99 standards use parameter and argument. The following table should help you translate. This book, parameter argument. Other books, formal argument, formal parameter, actual argument, actual parameter. Keep in mind that when no confusion would result, I sometimes deliberately blurred the distinction between the two terms using argument to mean either. Question. I've seen programs in which parameter types are specified in separate declarations after the parameter list, as in the following example. Double average AB, double AB, return A plus B over 2. Is this practice legal? This method of defining functions comes from KNRC, so you may encounter it in older books and programs. C89, C99 support this style so that older programs will still compile. I'd avoid using it in newer programs, however, for a couple of reasons. First, functions that are defined in older ways aren't subject to the same degree of error checking. When a function is defined in the older way and no prototype is present, the compiler won't check that the function is called with the right number of arguments, nor will it check that the arguments have the proper types. Instead, it will perform the default argument promotions. Second, the C standard says that the older style is obsolescent, meaning that its use is discouraged and it may be dropped from C eventually. Question. Some programming languages allow procedures and functions to be nested within each other. Does C allow function definitions to be nested? No, C does not permit the definition of one function to appear in the body of another. Among other things, this restriction simplifies the compiler. Question: why does the compiler allow the use of function names that aren't followed by parentheses? We'll see in later chapters that the compiler treats a function name not followed by parentheses as a pointer to the function. Pointers to function have legitimate uses, so the compiler can't automatically assume that a function name without parentheses is an error. The statement print pun without a parentheses is legal because the compiler treats print pun as a pointer and therefore an expression, making this a valid, although pointless expression statement. Question: in the function call f, a, and b, how does the compiler know whether the comma is punctuation or whether it's an operator? It turns out that the arguments in a function call can't be arbitrary expressions. Instead, they must be assignment expressions, which can't contain commas used as operators unless they're enclosed in parentheses. In other words, in the call f, a, comma, b, the comma is punctuation. In the call f, parenthesis, parenthesis, a, comma, b, parenthesis, parentheses, it's an operator. Do the names of the parameters in a function prototype have to match the names given later in the function definition? No, some programmers take advantage of this fact by giving long names to parameters in the prototype, then using shorter names in the actual definition. Or French-speaking programmers might use English prototypes, then switch to more familiar French names in function definitions. I still don't understand why we bother with function prototypes if we just put definitions of all the functions before main were covered, right? Wrong. First, you're assuming that only main calls the other functions, which is unrealistic. In practice, some of the functions will call each other. If we put all the function definitions above main, we'll have to watch their order carefully. Calling a function that hasn't been defined yet can lead to big problems. But that's not all. Suppose that two function calls each other, which isn't as far-fetched as it may sound. No matter which function we define first, it will end up calling a function that hasn't yet been defined. But there's still more. Once programs reach a certain size, it won't be feasible to put all the functions in one file anymore. When we reach that point, we'll need prototypes to tell the compiler about functions in other files. Question: I've seen function declarations that omit all information about parameters. Double average. Is this legal? Yes, this declaration informs the compiler that average returns a double value, but provides no information about the number and types of its parameters. Leaving the parentheses empty doesn't necessarily mean the average has no parameters. In K and RC, this form of function declaration is the only one allowed. The form that we have been using, the function prototype in which the parameter information is included, was introduced in C89. The older kind of function declaration is now obsolescent, although we still allow it. Why would a programmer deliberately omit parameter names in a function prototype? Isn't it easier to just leave the names? Omitting parameter names in prototypes is typically done for defensive purposes. If a macro happens to have the same name as a parameter, the parameter name will be replaced during preprocessing, thereby damaging the prototype in which it appears. This isn't likely to be a problem in small programs written by one person, but can occur in large applications written by many people. Question: is it legal to put a function declaration inside the body of a function? Yes, here's an example. int main void, double average, double A, double B. This declaration of average is valid only for the body of main. If other functions need to call average, they'll need to declare it. This declaration of average is only valid for the body of main. If other functions need to call average, they'll have... This declaration of average is valid only for the body of main. If other functions need to call average, they'll each have to declare it. The advantage of this practice is that it's clear to the reader which functions call which other functions. In this example, we see that the main function will be calling average. On the other hand, it can be a nuisance if several functions need to call the same function. Even worse, trying to add and remove declarations during program maintenance can be a real pain. For these reasons, I'll always put function declarations outside function bodies. If several functions have the same return type, can their declarations be combined? For example, Since both printPun and printCount have void as the return type in the following, is the following, for example, since both printPun and printCount have void as the return type, is the following declaration legal? Void printPun void, comma, printCount, int n. Yes, in fact, C even allows us to combine function declarations with variable declarations. Oh, nice. Double for values, also double for this function return type. Combining declarations in this way isn't usually a good idea, though. It can be easily confused. What happens if I specify a length for a one-dimensional array parameter? The compiler ignores it. Consider the following example. Double inner product, double v index 3. Double inner product, double with array of size 3, double array w size 3. Other than documenting that inner product's arguments are supposed to be arrays of length 3, specifying a length doesn't buy us much. The compiler won't check that the arguments actually have length 3. There's no added security. In fact, the practice is misleading in the fact that it suggests that inner product can only be passed arrays of length 3, when in fact it can be passed arrays of any arbitrary length. Why can the first dimension of an array parameter be left unspecified but not the other dimensions? First, we need to discuss how arrays are passed in C. As section 12.3 explains, when an array is passed to a function, the function is given a pointer to the first element in the array. Next, we need to know how the subscripting operators work. Suppose that A is a one-dimensional array passed to a function. When we write A index of I is equal to 0, the compiler generates instructions that compute the address of A index of I by multiplying I by the size of an array element and adding that result to the address that A represents. The pointer passed to the function. This calculation doesn't depend on the length of A, which explains why we can omit it when defining the function. What about multi-dimensional arrays? Recall that C stores arrays in row major order, with the elements in row 0 stored first and the elements in row 1, and so forth. Suppose that array A is a two-dimensional array point parameter, and we write array A index I index j equal to 0. The compiler generates instructions to do the following. 1. Multiply I by the size of a single row A. 2. Add this result to the result of A. 2. Add this result to the address that A represents. 3. Multiply j by the size of an array element. And 4. Add this result to the address computed in step 2. To generate these instructions, the compiler must know the size of a row in the array, which is determined by the number of columns. The bottom line, the programmer must declare the number of columns in A. That's why when we're declaring arrays, we could omit the rows, but we could give columns. We have to declare columns. Why do some programmers put parentheses around the expression in a return statement? The examples in the first edition of K&R, the C programming language, have the examples in the first edition of Kernighan and Ritchie's, the C programming language, have parentheses and return statements, even though they aren't required. Programmers and authors of subsequent books picked up the habit from K&R. I don't use these parentheses since they're unnecessary and contribute nothing to readability. K&R apparently agree. The return statement in the second edition of the C programming language lack parentheses. What happens if a non-void function attempts to execute a return statement that has no expression? That depends on the version of C. In C89, executing a return statement without an expression in a non-void function causes undefined behavior, but only if the program attempts to use the value returned by the function. In C99, such a statement is illegal and should be detected as an error by the compiler. How can I test main's return value to see if a program has terminated normally? That depends on your operating system. Many operating systems allow this value to be tested within a batch file or a shell script that contains commands to run several programs. For example, the line if error level 1 command. In a Windows batch file will execute command if the last program terminated with a status code greater than or equal to 1. In Unix, each shell has its own method for testing the status code. In the Bourne shell, the variable $? contains the status of the program run. The C shell has a similar variable but its name is $status. Question, why does my compiler produce a control reaches end of non-void function warning when it compiles main? The compiler has noticed that main, despite having int, has its return type, doesn't have a return statement. Putting the statement return 0 at the end of the main will keep the compiler happy. Incidentally, this is good practice even if your compiler doesn't object to the lack of a return statement. When a program is compiled using C99 compiler, this warning shouldn't occur, and C99 is okay to fall off the end of a main without returning a value. The standard states that main automatically returns 0 in this situation. Question. With regard to the previous question, why not just define main's return type to be void? Although this practice is fairly common, it's illegal according to C89 standard. Even if it weren't illegal, it wouldn't be a good idea, since it presumes that no one ever will test the program's status upon termination. C99 opens the door for legalizing this practice by allowing the main to be declared, quote, in some other implementation defined manner, close quote, with a return type other than int or parameters other than those specified by the standard. However, any usage isn't portable, so it's best to declare main's return type to be int. Question. Is it legal for a function f1 to call f2, which then calls f1? Yes. This is just an indirect form of recursion in which one call of f1 leads to another, but make sure that either f1 or f2 eventually terminates. And boom. Awesome. Let me scroll back up to the top of the chapter here. All right, you guys, that was chapter 9, functions in C Programming, a Modern Approach, second edition by K.N. King, which covers both C89 and C99. We've been teaching ourselves C programming from scratch here live on the channel. If you guys enjoyed this read-along of the stream, please like and subscribe. You can find a total breakdown, or if you want to, hold on. Oh, whoops. Didn't mean to do that. I think that glitched out my my thing here. Okay, well, whatever. If you want to follow along the, what do I want to say? Whatever. Okay. The notes that you see on the right side of my screen can be found within my GitHub in the description. What else? What else? What else? I was going to say something else. Oh, I forgot it. This has been the condensed version of the live stream. If you guys would like to see the full unedited version of me reading this chapter and solving the problems, consider jumping on the live stream where I teach myself how to code in both C and Python almost every single day. Cool. All right, you guys, this was chapter 9, wrapped up in C Programming, a Modern Approach, second edition by K.N. King. Thanks so much for being here, and I'll see you guys in the next one. Peace. All right, cool. Stop that recording. Nice. Let's go. Solid, solid, solid. All right, you guys, thanks so much for joining me tonight. Appreciate you guys being here. I'm going to hop off. Going to grab myself some dinner, whip up some salmon. A little filet. I got it in the freezer. Awesome. We'll be back soon to start completing some of the exercises for chapter 9, which was on functions. So really great stuff. Thank you guys so much for being here, and I'll see you guys tomorrow. Bye, guys.